everyone. My name is Juan. I'm a machine learning engineer at Unity Technology. So today we're going to talk about like training, like game AI using machine learning, or to be more specific, deep reinforcement learning. So maybe like before we start, I just want to see like how many of you guys over here are familiar with machine learning? Can you raise your hand? Well, that's a lot of people. How many of you guys are familiar with deep reinforcement learning? Oh, great. Okay, so like if you're not familiar with those, I'm gonna cover some of the basic concepts in machine learning as well as deep reinforcement learning. So here you can see there are like two games which are super popular in the AI world in recent years. On the left side, we have Dota 2. And on the right side, we have the traditional Chinese board game, which is called Go. And both of those games are super hard to master. And like we have hundreds and hundreds of hours devoted to both of these games from different peoples. And in the game AI industry, we kind of like try to solve them using traditional AI. And as you can see, since these games are super hard to master, using traditional game AI would be super hard to master. That's why like those two big research groups, such as OpenAI and DeepMind, they've tried to tackle these problems using the machine learning, or to be more specific, deep reinforcement learning. And actually, they've achieved game AI that can actually compete with the best in the field. And also, like for some of you who might be familiar with Unity, Unity is a cross-platform game engine which is like super popular, and we already have like more than 50% of new mobile games made by Unity, and also more than 60% of the AR or VR contents created by Unity. So you can imagine like using this game engine, you can create any kind of content you want, 3D or 2D. As you can see, like we have those famous games like Hearthstone or like King of Royals, Flappy Bird, Overcooked. All of these games are created by Unity. So you can imagine like if we combine the reinforcement learning power with the game engine, that would be super helpful. So that's what we at Unity do. We kind of take all of these recent research advances, and also we try to combine it with the power of the game engine, and we open source it into this open source project. So like you can, just like today, you can just go to this link, download this open source project, and the talk over here, we are mainly focusing on what this open source project can give you. And all of the content we are gonna talk about today, you can get them for free online on GitHub. Okay, so we will just like go through how the workflow usually is. So initially we will set up our game. So if you're a game developer, you might be really familiar with this. But if even like you're new to this, it's super easy. Like Unity is like famous for easy to get on and like just making your own game. So usually we make our game and then we integrate the ML agents SDK into the game. And then we basically train. And you can see like usually we will set up multiple of these instances over there to train. And once we train and we get the machine learning model, we'll be able to embed the model into our game, and we can ship it on any of the platform we want. For example, mobile platform or like Xbox, Switch, whatever. So maybe I'll just like first focus on how do we integrate ML agents into our game. So before I dive into that, I'm gonna first introduce the concept of agent. So for any of you who are familiar with reinforcement learning, you might be already familiar with what agent is. So agent is basically the thing that are in an environment, and it can observe the game state and take some observation from the game or from the environment. And then it's gonna have its own policy. And then based on this policy, it's gonna like be able to yield some action. So you can consider this policy as some sort of function. So it can be a random function which like just ignores the input and it can just like generate some random action or it can be something that are hard-coded. For example, if I see red, I go left. If I see yellow, I go right, something like that. And if it is deep reinforcement learning, then it's basically using deep neural network as this function. So let's take an example over here. So for example, we have some input or we have some observation over here, such as like position of some objects, velocity of some object, or rotation of some object. We take this and then we feed that into the neural network. And you can imagine this neural network be able to generate some output, and we will map them to the action. So that's basically how like you set up everything in the game, or like how ML agents is helping you to set up everything. And once you've set up this, you just like feeding the reinforcement learning signal, and it's able to train and generate the corresponding model for you. So once you have the game, you'll be able to generate this neural network and connect it to multiple of the agents. So over here you can see like we have 12 boards over here. Each of them will have its own observation and will be able to take the corresponding action according to what its observation is. And all of them are connected to this one neural network, which generates one singular behavior. Also on the right side, ML agents is also able to help you generate multiple of the neural network based on the setup you give it to. So over here you can see there are two kinds of cubes over here, or two kinds of players on the soccer field. One is the defender, which are standing in front of the goal, and also like we have the attacker, which are moving more freely. So those two type of cubes, they are using two type of different neural network. Okay, so basically that's how we set up the ML agents. Of course, there are more technical details, and if you're interested, you can go to the open source project. Next, I'm gonna go to the training part. Once we've set up the game, how do we actually do the training? So usually in the ML agents toolkit, we provide two type of training methods. One is the reinforcement learning method. So you can see like we have our environment or the game over here. And then we feed the observation as well as the reward into the agent. And the agent will have its policy, and it will be able to generate the corresponding action. But how do we know, or how do we guide the agent to provide the optimal or the desired action we want? So basically, it's really simple. We just look at the reward. When we take a certain action, we will see, okay, like maybe it's positive reward or negative reward. If we have some series of action that gives the positive reward, then we will just increase the possibility of the corresponding action. Or on the contrary, if we have some negative reward, then we will just like attenuate the probability of that series of actions. So that's how we guide our actions, and eventually we'll be able to get some optimal action series. So that's how reinforcement learning works. So I'll like give this example to like showcase how it actually works. So basically we have this game. We have this yellow chicken over here, which is trying to cross the road, and also it's gonna like try to pick up as many gifts as possible while avoiding to hit the car. So over here, the observation is basically all of the pixels in this frame. And the action it's allowed to do is the right, left, up, or down actions. If it hits a vehicle, it will get negative reward. If it's like picking up the gifts, it's gonna get positive reward. So initially, before the training, the chicken is just moving randomly. It doesn't know like what gifts are, it doesn't know what vehicles are, it just like moves around. So after 1 hour of training, it's starting to know, okay, like picking up gifts are good and avoiding vehicles are bad. That's why it's starting to learn the gist of like how to act optimally, or how to act according to our reward setup. So you can see like all of its input are just like pixels in the frame, and it's able to learn that. So after 6 hours of training, it's able to pick up the GIFs in a really efficient way, and sometimes like it just like sees all of the vehicles and goes really fast, able to pick up all of the GIFs along the way. I don't think like any human will be able to do that, but yeah, that's like how. Yeah, that's sort of like the powerness of like the power of reinforcement. Okay, so we also provide another type of algorithm within the ML agents toolkit. That's imitation learning. So I guess like many of you are familiar with supervised learning, which basically provides a label and provides an input. That's the same in the game. So when we are playing a game, at any time step, we'll be able to know what are the game state or what are the observation of the game, as well as what are the action the player actually took. So that's a pair of input versus the label. So we kind of store that into this observation action pair as the supervised learning data. And then we will feed that data into the agent's policy, which is the neural network over here, and train that neural network. And that's how imitation learning works. So I'll give you also an example of how it works. So on the left side, we have the human playing. At any time step, it's able to have some kind of observation based on the track, its own speed, where it's like stuff like that. So it's generating those data and it's feeding into this data store. And on the right side, we have the machine, which are keep updating its model using that data. And you can see like initially it will just like sometimes hit the track because it doesn't know in certain occasion what to do. But after a while, it's starting to pick up the stuff and it's starting to learn, okay, like on this track, what are the direction I should move and how do I drive safely in this track? So usually in these sort of like simple scenario, actually just take a couple of minutes and we'll be able to learn how to drive on these tracks. So really quick and pretty fast. Okay, so these are the two types of training methods we've talked about. One is the reinforcement learning, another one is imitation learning. Reinforcement learning like learns through the rewards we've provided as game developers. And it takes a lot of trial and error until we reach the optimal policy. And also like simulation, we usually will speed up the simulation because like given faster simulation, we will be able to generate the data faster to basically train faster. And also like potentially it's able to surpass the ability of the human. And that's how in Dota 2 or AlphaGo, how those research groups were able to generate AI that surpasses human beings. On the right side, we have imitation learning. Usually agents will learn through demonstration in imitation learning, and it will take much faster time for the training to happen. However, it's only able to generate AI as good as human, and it cannot surpass human. Okay, so these are the two drawbacks. Reinforcement learning is relatively slower. If we use imitation learning, usually the demonstration is limited and also the agent cannot do better than human. So how do we solve this? We can potentially combine reinforcement learning with imitation learning. So we will, at the same time, generate those observations as well as having this reinforcement learning loop. And if we combine those two, we can potentially use demonstration to guide the agent to explore better, as well as doing reinforcement learning to make it potentially surpass the human. So that's like, yeah, RL plus IL. And so all of these algorithms are offered within the ML Agents toolkit. And also we have all of these training examples which are offered for free in the open source project, and you can download it if you want. And I'm gonna demonstrate several of them because like different ones will showcase different algorithms we've provided within the open source project. So I'll first showcase our really simple environment, and I'll actually give a short demo of how we actually trained live. So in this game, the goal is basically for those balancing heads to balance the ball on top of the head as long as possible. And observation is the platform's orientation, where the ball is, and the ball's velocity. And also the actions are basically the rotation. Rewards are if you keep the ball as long as possible, like longer you keep it, more rewards you'll get. So after training, it will be something like this. After training, it's able to balance the ball really well. And I'm going to show you like on live how it actually works. The training only takes several minutes. So I'm going to open my Unity editor. Here are the game scene, and I'm able to control all of the heads over here using my keyboard. So I can tilt left or I can tilt right. And it's really simple to set this up. So this is like purely controlled by me. And if I'm gonna use reinforcement learning to train, how do I do it? I go to command line and run this command, which basically spins up a Python process, which has TensorFlow within it. And all of the trainer code you don't need to write yourself because we've written it for you. So you just like say, okay, I'm gonna start this Python process which has the model in it, and it's gonna be connected to the Unity editor. And I click play over here. So you can see like it's doing simulation in real time, and it's trying to balance the ball as good it can be. And since it is reinforcement learning, we try to speed up the simulation so that the training becomes faster. And also we have multiple of these agents so that we have 12x speed up. But like if you want to just like do one of them, it's totally fine, but it will just like be slower. So you can see like as we are training, we will calculate the mean rewards over here, and it's slowly increasing. And you will be able to see that like it's starting to pick up the skill. It's starting to learn, okay, like maybe I should tilt right or left in this occasion, and it'll be able to learn the balancing. So yeah, just take a couple of minutes. So now the mean rewards are already 5. You can see like for some of the heads, the ball just like will stay there for a few seconds. You can see the gist of it. So eventually the reward will reach 100, and it's able to balance the ball really well on its head. You can see like this takes really like only a couple of minutes, and we will be able to learn a model. Then we can basically embed this model back into the new game and use this model inside the game. Okay, so I'm going to stop the demo here. So that's our most basic environment, but we also have other environments such as this one. So you know, like as human, we learn by starting from simple over to more difficult tasks. And that also applies to reinforcement learning. So that's why we've embedded the curriculum learning within the ML agents. So usually you will start, like teach the agent to start from single task. In this case, we will start from having no wall at all. And then slowly, as the agents start to pick up the gist of the game, we will slowly increase the height of the wall. And then the agent will be able to learn to pick up more difficult tasks, and eventually it will be able to learn to step on the box and then jump through the wall to reach the target. So I'm going to show you how it performs. So you can see like we are kind of like changing the height of the wall, and the agent is able to pick up this behavior of stepping on the box and then jumping through the wall. And we have no hard-coded rules over here. All of these are automatically generated using reinforcement learning algorithms. Also, we can utilize this concept of memory. So for many of you who are familiar with machine learning, we know LSTM, which are basically memory cells. And agents, if you don't use LSTM, they don't have memory. They can only see the current timestamp. But if we use LSTM, it's going to be able to memorize what it has seen. So over here, this little cube, our agent, is able to see this target, and given its color, it's going to be able to remember the color, and then go to the corresponding target. So it will be able to say, okay, like I see orange, that's why I go to the orange target. So if it sees an orange target, it will just like go to the orange target. If it sees a yellow, it will just like go to the yellow. So we also have multi-agent capability, which is like if we set up this adversarial scenario, we can potentially embed multiple of the neural networks within the scene. So in this case, we've created two types of reward setup. One is to reward more towards entering the opponent's goal. Another one is towards defending. And if it loses one goal, it will get like larger negative reward. So if we combine them into the same scene, it's able to generate two types of behavior. And that's what we've seen before, the soccer environment. And you can see like, just like, actually we didn't place these agents over here. We just like give them different reward setup, and they are able to generate those two types of behaviors. Right. So the next one is curiosity. So many of you know, like human, we have curiosity, even if like we don't immediately receive some benefits, we'll be curious if we find something new. And that also applies to agents. So in some of the environment, especially for those really sparse reward environment, it's very hard for the reinforcement learning agent to learn any behavior. But if we give it curiosity, which is basically rewarding the agent for seeing something new, it'll be able to learn some behavior much faster, or being able to learn behaviors that were not possible before. So this is like motivated by this paper published by Zach. It's called like curiosity-driven exploration. We just take the idea from the paper and implement it in our open source project. So you can see we've created this environment which are super reward sparse to showcase our algorithm. We will have 9 rooms, which is like super big for an agent. And we will have this purple switch within the scene, and we will have 6 stone pyramids. And once this purple button gets pressed, one of the pyramid will turn into golden. And then if the agent learns to knock over the pyramid and get the target, it will get rewarded. So you can see like this is super sparse, but if we use curiosity module, we'll be able to learn the behavior. So this is like when we turn the curiosity off, the agent just like knows to, I don't know, like lean against the wall and just wandering randomly, because it hasn't found a way to consistently find the reward. However, if we turn the curiosity module on, it will learn to actually step on the switch and then find the golden pyramid and knock it out, and also like get the target. so that's like some of the features that's like included in the open source project, and we also have other features included in the project. For example, on-demand decision, which are basically saying, okay, like not at every timestamp do you need to actually give it an action. You only need to give action at certain point, and I'm going to tell you when do you get the action. And also SAC, which are off-policy algorithm, which like just increase your example efficiency, and also Gale, which is basically IL plus IL. Yeah, so these are all of the features. So I'm gonna quickly go through some of the other. Yeah, so this is our game upload, and you'll be able to see like over here our. So this like cuteness of the dog is totally driven by machine learning. It's not some generated animation. All of the joints are driven by machine learning or like reinforcement learning in this case, and it's able to walk along inside the room and pick up the stick and stuff like that. And also the performance is really good. So on a mobile device, we are able to simultaneously generate 50 of the dogs, which are basically like doing inference for 50 of the agents, and they're performing really well. And you can see the frame per second is like 50. If we have 10 dogs and even more, like it still like generates a reasonable FPS. Okay, so we also have a bunch of collaborators, especially our game studios. And we've actually collaborated with their games and embedded our ML agents models into their game. So this is a game studio called What Up, and they've made this game, which are sort of like this combating game. It's like a real-time warm combating game. The target for the agent is to grab those red crystals and then take them home. And the movement of the agent over here are totally driven by machine learning model. Yeah, so like they will be able to like know, okay, like now I need to move here and pick up the crystal and take them home. And this game is already live on Xbox. Also, we have collaborated with another game studio called Jam City. Maybe you've heard of Snoopy Pop, and that's our like main collaboration game. It's a bubble shooter game, which are similar to this, and basically when we are setting up the like ML agents training, we are using observation of the pixels over here, and we are giving it like 20 angles of actions, and then giving it reward for canceling the bubble or freeing up the birds up over there, or getting more scores. So before the training, you can see like the agent is just shooting randomly over here, doesn't know what to do. But after a while, it's able to pick up the training. Yeah, I'm gonna speed up. Anyway, like after training, it's able to pick up the patterns and be able to solve this game. Also, we have collaborated with the game studio from Sweden, and their game is called Source of Madness. It's a horror game, and within the game, they were able to generate those super horrifying monsters, and all of the joints in the game are controlled by machine learning models. Okay, yeah, you see all of these monsters over here. All of the joints of those monsters are driven by ML agents. If you give it a slightly different reward, those monsters will generate a different behavior. For example, jumpy monster versus like crawling monsters, stuff like that. so I'll just skip through this part. And also we have lots of community created contents. For example, over here we have machine learning models guiding the behavior of those ants, and potentially we can have like hundreds of ants crawling together, and they're able to get the stock and also like try to explore as much as possible the area. And also we have those like self-driving scenario where, so over here these tracks are randomly procedurally generated, and machine learning models will be able to pick up the track and be able to drive on these like super dangerous tracks and be able to know, like, just like go through it and know how to go through it. Yeah, anyway. Yeah, if I have more time, I'll just like go through the video. But okay, so the last one is like the angry AI. So machine learning model is able to guide the crawling behavior of the robot, and they know to avoid obstacles while going to the target. So this is the training scene where we have this target, which is the red moving part, and the agent is able to just like go through this and like trying to get nearer to the target. And once it's trained, it'll be able to know how to just like move towards each other and start fighting. And yeah, in this scenario, they have like a really cool, fancy video made. Right. So, yeah. And also the last one I'm gonna introduce, like, so basically on Udemy, we have this course made by Immersive Limit, and they've set up this course so that you can just like learn from basics for Unity as well as ML agents, and you can just like, they will guide you through making this scene and also embedding the ML agents SDK into the scene, and then eventually be able to train the AI that can fly these airplanes and like through those targets. Okay, so that's it. And any questions?
So, is there another set of applications we can use these ML agents, GitHub for? Any other applications other than games?
So basically, you can use Unity to make any kind of simulation environment, not necessarily games, right? You can potentially like use them for example, self-driving scenario setup, and then you can train your own AI to guide your vehicle driving through those scenarios.
So you're training agents to solve problems in different games. I'm wondering to what extent you can use transfer learning to learn similar objectives. If like the game, say, like the two games are trying to just move to a slot.
Yeah. So like for transfer learning, you can potentially like just kind of like transfer the weights of a certain model into another model. But like usually like for those games, if you set them relatively well, like we don't necessarily use transfer learning because the model are so small and like pretty quick to train.
So for the models, are they all instantaneous and you're doing probabilities of each motion based on the current state, or is there some memory?
Yeah, so if you use the LSTM, or like we also have like frame stacking, which are basically, for example, for the previous 5 time steps, what are all the observations over there. So if you use LSTM or frame stacking, you can have memory. Otherwise, you can only have the current time steps observation.
So for the demos that you're doing, which it?
Oh, so usually most of these are not using memory at all.
Okay.
Oh, yeah. You guys have any other questions? Like if.
Well, thank you guys very much. Give it up for a wonderful presentation from Jan. Thank you. Now you realize that Unity may be a part of your AI stack.
Hi, I'm ex-Unity. I was part of Unity.
Wow.
Thank you.